Bit flip, Trans-Vernam cipher. Transmitter here, recipient here. What goes through are zeros and ones. We take the symbol 0 and match it with a string of bits, 6 bits. And we take the symbol 1 and match it with 6 bits, different string. Now, from the standpoint of the recipient, we measure Hamming distance. In other words, the recipient is expected to get a string of 6 bits and then compare it to those 2 strings to check if the Hamming distance is exactly 3. What's the Hamming distance? The number of bits that the identity is different between this string and this string. So if we take here this string here, 110, 110, and we change this to 1, and this we change to 0, and this we change to 0, then this string has a distance of 3, Hamming distance of 3 from this. That's Hamming distance. Now, the string of 6 bits that comes to the recipient checks if there is a distance of 3 between what comes in from the transmitter and the symbol 0 and the symbol 1. There are 4 possibilities. Either there is no distance 3 but any other distance, 1, 4, 0 for both, or a distance 3 from the 0 and something else from 1, or the opposite, a distance 3, 4 relative to this string that represents 1 and something else, a different Hamming distance from this string, or both have a distance 3. Now, here is the key. If the case is this, then the recipient here will interpret this message as sending the symbol 0. So we use 6 bits to send 1 bit, 0. If this is the case, then the recipient will say, I received the message 1, and interpret this string as 1. If this is any of these other cases, any of them, the recipient discards, ignores, moves on. So now the transmitter can send 6 bits, 6 bits, 6 bits, many strings of 6 bits. Most of them can be nonsense, will be such that will be interpreted by the recipient as garbage. Some will be interpreted as 0, and some will be interpreted as 1. And the recipient then will take the combination of zeros and 1 that are meaningful and read the message that the transmitter sent to her. But if you are a hacker, even if you are armed with quantum computer, all these strings are candidates for information. Why? Because you don't know the key. This is the key, these particular strings. And when the transmitter embeds the real message in a larger, maybe much larger, actual message, then we can prove mathematically that you have enough equivocation to hide the identity of this message, regardless of the computing ability of the attacker, quantum or otherwise. This simple hiding of information in a larger stream allows two communicators to hide the pattern of their communication. The transmitter can send, let's say, 1,000 bits per second all the time, 1,000 bits per second, 24/7. The actual communication, if we draw a graph here that says that over time, these are the 1,000 bits per second, only these are the bits that represent actual message. Here, that's the pattern. Or perhaps it is like here, where most of the 1,000 bits have meaningful information. And maybe the pattern changes. Things becoming heated, you talk more. Less heated, you talk less. A lot of the hacking happens through detecting changes in pattern of data transmission without understanding the contents. This is being eliminated using Bitflip. Now let's add another twist. Instead of one recipient, we have two recipients. How does it work? Well, we equip the first recipient here with particular 6-bit string for the 0 and the 1 for their input, and the other recipient we equipped with a different string of zeros and 1 for their interpretation of a symbol 0 and a symbol 1. And now when a 6-bit string comes from a transmitter, it can be that the Hamming distance of 3 is true here, not here, not here, and not here. What happens then? The first recipient will say, oh, I got the letter 0. The second recipient will say, garbage. No Hamming distance of 3. The next 6-bit will be like this. What will happen then? The first recipient will say, garbage, I ignore it. The second recipient will say, oh, I got the letter 1. So what happens? We have a single stream of bits interpreted one way by one recipient and different way by another recipient. Each of them using their own key. What does it mean from hacking standpoint? It means that if that is what you have, the ciphertext, equipped with quantum computers, I don't care. That's what you have. You cannot decide either one of them if they receive this message, the message that's based on this key, or the message based on that key, because the key is not included in the ciphertext. In all the ciphers of modern cryptography, the key is very deeply, in a very complex way, we hope, embedded in the ciphertext. And that's why we cannot really sleep at night, because we don't know if we are being attacked by someone smart enough to dig out the key. Here, There is no question about it. The key is not inside the ciphertext. And we don't have to have two recipients. We can have 10, 100,000. The length of this string is 6 or 10 or 60 or 1,000, can grow and grow. And if you read the article referred to at the end of this video, you will see the exact analysis of why we can use a key of sufficient size and embed a message in sufficient amount of garbage, so to speak, that we can go to sleep quiet to our sweet dreams, not afraid of any quantum computer hacking us. The Hamming distance of 3 was used because the size of the string was 6. It has to be half of the size of the string. If we have a string of n bits to represent the 0 and the 1, then we will flip half of them. Why half? Because the new string with half of the bits flipped from the hacker's point of view will mean that every bit that they see has the same chance to be the bit as written or the opposite. Because he would know that 50% of the bits are flipped, so the chances are half-half. And the number of possible strings that have a Hamming distance of half of n from this string is enormous. Now, we checked bit flip from the recipient point of view. What happens from the transmitter point of view? Let's say the transmitter wants to send the symbol 0 to the recipient. Transmitter will have a copy of the string that represents 0 for the intended recipient, use a random number generator to randomly flip 3 bits here. So let's say gets this one. So this string has a Hamming distance of 3 from the original. That's guaranteed because you flipped 3. Now the transmitter will check the distance between this and the string that represents the symbol 1 for the same recipient. And check if this distance that it computed is 3. If the distance is 3, then it goes back to the random number generator to flip again, randomly, 3 bits, and try it again. Now, the transmitter can say, okay, I flip and discard it, or I flip and send it to the recipient. The recipient will not be confused because the recipient will say, oh, the distance 3 is from both 0 and 1. For me, it means it's garbage, and ignore it. The hacker will not know. And so it goes here as many times as needed. Eventually, it finds a combination of flipping that the distance from the strings that represent 1 is other than 3, and then it will send it to the recipient. That's how it works. Now, like I said, the size of the string is much greater than 6 and determines the security that you project. But the security can be at Vernam size or below, but it is credibly estimated by simple probability calculus. So we have here a new approach to project security with randomness, with credible assessment of the security, and with the ability to, for the user, to increase the security to mathematical secrecy, which is the highest. These are capabilities that will serve us for the Internet of Things, for digital money, and for a myriad of applications, all while safe and secure from any attack by quantum computers. Stay tuned for more.